Good afternoon. Today my group, Nicole Bezic, Jeff Borsick, Velena Ho, Toko Nagata, and I will present our analysis of the Blue Ribbons food case and our answers to the case questions. First of all, let's go through the case situation. The case is about the medium-sized company Blue Ribbon Foods and its decision regarding how much of each of their tomato products to produce. There are two different grades of tomato that are used in differing proportions to make either whole canned tomatoes, tomato juice, and tomato paste. Management is trying to find the optimal mix of products and grades to maximize profits. Currently, management is struggling because of some fundamentally flawed analysis they have conducted. Here are some of the current ideas that management has come up with to solve the problem. Allen correctly states that whole tomato production is limited to 800,000 because that is the maximum number that can be produced with the current tomato order while maintaining the required quality grade of 8 for whole tomatoes. Haneda's suggestion to use the whole crop for whole tomatoes is a poor one because the whole tomatoes need to have an average quality grade of 8. With the current order of tomatoes, the average quality is 5.8, which is significantly lower than the required 8 for whole tomatoes. Reynoso's analysis of the situation is flawed because he thinks the price of tomatoes is directly correlated to their quality. This leads him to believe that grade A tomatoes are 9/5 times the price of grade B tomatoes. This is incorrect, so using this he comes up with incorrect marginal profits for each product. Because of this, Reynoso overvalues tomato paste and undervalues whole tomatoes and tomato juice. This is why he thinks Blue Ribbon should make more paste than it actually should. Next, Jeff is going to talk about linear programming.
We established these decision variables given here so that we can manipulate the ratio of high quality and medium quality tomatoes that are used to make whole tomatoes, juice, and paste. We also established our unit of measurement as pounds of tomatoes, and we'll use this unit for the rest of the programming. Going down the list, we have the variable AX to represent how many pounds of A tomatoes in the whole tomatoes, BX for how many pounds of B grade in whole tomatoes, AY and BY for how many pounds of grade A and B respectively in the juice, and lastly AZ and BZ for the poundage in tomato paste. The objective function in this case was to maximize profits by using the tomatoes in the most efficient way possible. The coefficients of $4.44, $3.96, and $5.53 were taken from figure 3 of the case and represent the profit of selling the tomatoes as whole, juice, or paste. Lastly, for the linear program we have the constraints. These quality constraints represent the minimum quality of tomatoes that must be used for whole, juice, or paste production. Because demand is not infinite, we also have the demand constraints, with the biggest demand by far being for the whole tomatoes. And finally, because we do not have an unlimited supply of tomatoes, there is a constraint on supply, with 600,000 grade A tomatoes and 2.4 million grade B tomatoes. Here is the information that I just stated in its Excel spreadsheet format that you can view at your own convenience. And next, I'm going to hand it over to Nicole, who is going to discuss the optimal solution.
The results after plugging in the appropriate calculations into the solver showed our optimal solutions. The results demonstrated that the total amount of pounds for each product were 525,000 pounds of grade A and 175,000 pounds of grade B whole tomatoes. The results for the optimal amount of tomato juice were 75,000 of grade A tomatoes and 225,000 pounds of grade B tomatoes. Meanwhile, the amount of pounds for the tomato paste were 0 pounds of grade A tomatoes and 2 million pounds of grade B tomatoes. The results for the total amount of each product produced were 38,889 cases of whole tomatoes, 15,000 cases of juice, and 80,000 cases of paste. The results for the actual quality of each type of tomato used were 8 points for whole tomatoes, 6 points for juice, and 5 points for paste. Lastly, our actual net profit resulted in a total of $134,466.67. And now Velena will discuss results of the sensitivity report.
Sensitivity analysis gives us an indication of how changes in availability of resources and changes in profit affect the optimal solution. The first question we considered is if the company should buy 80,000 more pounds of grade A tomatoes available at 85 cents per pound. Since the report shows us that the shadow price is 0.271 and 80,000 is within the allowable increase of 600,000, this means that 80,000 more pounds of grade A will increase the objective value or profit by $14,808, or 80,000 times 0.271. The company should therefore buy all of the additional available pounds of A. The second thing we considered was whether or not the company should pay for an ad campaign that would increase juice demand by 25,000 cases. Since BRF is already using all of its available crop, it would be unable to meet such a jump in demand and should not invest in the ad campaign. The third question we looked at is whether the optimal solution would change if the price of juice increased by 30 cents per case or 0.015 cents per pound. 0.015 is within the allowable increase, so the optimal solution for our decision variables doesn't change. However, the objective value, or profit, does increase since each case of juice brings in more profit. Lastly, we considered how much the company should pay for an additional 50,000 pounds of grade B tomatoes. Since 50,000 is within the allowed increase, the profit would increase by 8,683, which is 50,000 times the shadow price. BRF should therefore only be willing to pay anything less than 8,683 for the extra tomatoes so that the extra profit is more than the cost. This concludes our analysis of the Blue Ribbons food case, and we suggest considering the optimal solution that we found in Excel.